Hello, I'm Joe Giuliano, and today I'm presenting Lab 4, Magnetic Field of Permanent Dipole Magnets. Here's our introduction. So in this lab, we calculated the distance dependence of the magnetic field due to a small bar magnet. We did this to observe the distance dependence and dipole moment of the magnetic field of the bar magnet using an app on our phones called the magnetometer. And the result from this was a computational model in GlowScript, as well as an Excel sheet that we used to graph the magnetic field versus distance. Here are the principles and models utilized in this lab. We used Biot-Savart law, we used the magnetic dipoles, magnetic fields, and distance dependence. And then for our models, we used a GlowScript computational model, and we used an Excel graph. Here are the equations needed and used in this lab. So we used Biot-Savart law, which describes the magnetic field generated by a current. We used the magnetic field created by a dipole formula, which describes the magnetic field B, created by a dipole with magnetic moment U and observation location R. And then we also used the distance dependence of the magnetic field formula, as shown on the right. So here's our experiment. On the left, you can see we have a bar magnet attached to the meter stick, and then we have the magnetometer app orthogonal to the meter stick. And here are the steps on the right for completing this experiment. Here's our Excel data. So on the left, we have our graph that was generated from the data on the right, which we got from our experiment. And using this data, we can use the slope and the intercept given in this formula on the graph, and we use that to calculate the value of the magnetic or of the dipole moment to be 4.61 amperes per meter squared, or amperes meters squared. So here's the code that we generated using GlowScript, or the computational model we generated using GlowScript. And so in the top right, we have our initial conditions. So we have our mu naught over 4 pi, which is just our constant. And then we have our magnet, which is placed, as you can see in this image here. And then we have our mu hat, our mu magnetic, which is our magnetic moment. And then we have our magnet.mu, which we calculated here. Here below is the dipole magnetic field function, which we had to create ourselves. And then we have the computational model in GlowScript, as shown here, which shows the magnetic field. Here we have the data that was also generated. So we have our magnetic field magnitude, which is only in the x direction, as shown here. We have our distance, which is 0.27 meters. And then we have our magnetic field from 45 degrees, which is this part here in the top right in pink. And so here are what if questions. So if we hadn't oriented our experiment to compensate for magnetic north, we would have had the magnetic field of the Earth and the magnetic field of the bar magnet included in our calculations. And because of that, we wouldn't know which was due to the magnet and which was due to the magnetic field of the Earth. So it would mess up our calculations. And if we were to stick two identical magnets together end to end, due to superposition, the total magnetic field would be increased, resulting in most likely increased distance measurement. And to conclude, so in this lab, the distance dependence of a bar magnet was measured using a meter stick and a magnetometer smartphone app. Utilizing a graph created in Excel, using data from our experiment, we calculated the dipole moment of the bar magnet to be 4.61 amperes per times meters squared. Additionally, a GlowScript computational model was created to visualize the magnetic field of the bar magnet. And here are our assumptions and sources of error. So we assumed the phone was facing directly north when performing our experiment. We assumed the bar magnet and Earth were the only objects in our system, as in no other magnetic objects were affecting our system. And then our sources of error could be other smartphones nearby, being done indoors, and the accidental bumping of a phone in the experiment. And that's it. Thank you.